Okay, hi. So my name is Eshed Galor. I will be presenting today with Omer Anson, the Dragonflow PTL. And we'll be talking about scaling the OpenStack networking to beyond 4,000 nodes with Dragonflow. No, it doesn't work. Doesn't matter. Okay, so the question is Neutron ready for production? And this question was asked also in the one before last OpenStack summits in Barcelona, and was answered by Mirantis. They have conducted a performance and scale test in December using the Mirantis operating system. And they had 3 hardware labs for testing. The largest one was just a little less than 400 nodes. And they were able to get line rate on the data plane. And they were able to spin up about 24,500 virtual machines. And they concluded that the SNAT Neutron works at scale. And this is basically the highlights of their test. So they had, on their largest lab, about 378 nodes. On each node, they had 125 heat stacks. On each heat stack, they had 196 virtual machines, a DVR router, and a subnet, one subnet. So they used the VXLAN, and the behavior that they observed was that around 16,000 virtual machines, the ARP tables exploded and they had to rescale them. At about 20,000 virtual machines, the RabbitMQ and the Ceph broke. And at 24,500, the services and agents broke. But even though the control was failing, the virtual machines were still able to communicate, so their integrity test was still working. However, that means that over this point, it's no longer production ready. So the question is it enough? Is a full OpenStack Perf for about 400 nodes good, good option? Is a maximum of 24,500 virtual machines per OpenStack reasonable? So what happens if we need more scale? What if we need to grow over 1,000 servers? Which is a use case that we see quite a lot right now. So the problem is, as we see from a Mirantis test and also from our test, is the OpenStack scalability is limited by the workload size. So that's a problem because you don't know what the workload size will be, right? So especially if you're a public cloud, you want the workloads to continue as far as you have resources, but you don't want the OpenStack to start crashing when you go over some number of virtual machines. That doesn't make sense. So the reason, at least for the networking part, is that the network control and services, they break at scale. There are various reasons for that. And the solution, at least for the networking, as we see it, is composed of 4 pillars. The first one is you need to separate the reads from the updates. This is actually a pattern that can also be used for other components in OpenStack like Nova, which also suffer from this problem. How we think about doing that is just to add a scalable read replica of the Neutron database instead of using Neutron for the reads. And use a well-distributed and well-scaling database like Redis. The other pillar is lean and distributed control plane. That means you manage small, even one virtual switch in each controller, and the control should be small. And that means not open daylight. The third pillar is to distribute policies instead of flows. If you look at networking OVN, so in OVN we are distributing flows directly to all the controls, to all the OVSs. And if you distribute policies and compile them into flows on the edge, that means you have a smaller footprint and you can grow with the workload and not with the infrastructure. And the fourth pillar is distributing the network services, which is what we will be talking about in this presentation. The idea is you want to run your services at the edge, meaning in a compute node, and you want to try to suppress all the control plane messages going into the network. And to leverage the predefined nature of the cloud, where you know before you start a VM where it's going to run and who is it going to communicate with, because you know all the topology in advance. So as an example, Dragonflow plus Redis. So the user does calls to Neutron API, creating, updating, and deleting mainly, and some reads as well, especially through dashboards and so on. These updates are written to the Neutron database, and then we have the Dragonflow ML2 driver, which is registered to all those updates, and it will update a Redis server. In this case, we support several technologies, but in this case, it's a Redis. And this Redis will be used as a read replica, for which we publish all the updates, and we use it to read all the topology changes on all the Dragonflow controllers, which are each is deployed on a compute node and controlling the local OVS directly. Now on the right side you can see this pie chart. So it's not accurate because it shows that you have 95% queries and just 5% updates from all calls to Neutron API. But this actually changes as you have more ports and more VMs, more Neutron ports. The red will shrink until it disappears, because each new port you add needs to be synchronized across all the compute nodes, and that means a lot of reads. So in Dragonflow we have, if you don't know Dragonflow, so Dragonflow is part of the OpenStack big tent. It's an implementation for Neutron. We have several services that are already distributed. You can see them on the squares below. And we will talk about 2 of them today. And we support currently 3 databases for the distribution of data, OBSDB, etcd, and Redis. And we also support 3, actually 2.5. One is still at work for publish and subscribe. We use ZeroMQ, Redis, and working on etcd. I think, yeah. Okay, so Omer will present 2 of our services.
Okay, so I'm going to present 2 services that we have written in a distributed manner. The first one is going to be SNAT. Does it work? Wrong way. Okay, so a brief overview of SNAT and DNAT. What you have is in SNAT is you have a virtual machine that wants to access a server somewhere on the internet. So it has to somehow receive a public IP. Now each virtual machine has a private IP in the private network, say, overlay network. And at somewhere on the way it has to go through a centralized SNAT service to get this public IP. Now in theory this service has to be centralized because you have one IP that has to be shared across all compute nodes in the entire cloud. If not one external IP, then a few external IPs. In DNAT, the issue is a bit simpler because each VM is given a single IP. This IP is not shared with other virtual machines on other compute nodes. So the compute node by itself can do the natting and unnatting, and then you don't need this centralized mechanism. The virtual machine can send the packet directly to the internet and have the compute node, for instance, do the NAT. Now, this is a different diagram of how this is done. You have a virtual machine that it wants to send out a packet to the network. So the packet goes to a network node in the middle, in which you have an SNAT unit that does the natting, and then it sends a packet out. Packet comes back again through the SNAT unit to be unnatted, and then sent back to the virtual machine. On the far side, you have an explanation of how, demonstration of how DNAT works. A packet comes in from the internet to the floating IP that belongs to the virtual machine. The compute node can do all the packet mangling at the compute node, and then doesn't have to go to the network node. This can already be done in a distributed manner. So how did we do this in a distributed way in Dragonflow? We said that what we built was we have each compute node, and the compute node does its own NAT, and then the packet after it has been NATed can go through some routers, which this is a mistake. It's not virtual routers, it is real routers that leads in the end to the one gateway that lead outside of the cloud, and then the packet goes to the internet. In effect, what we are showing here is that we have two NAT mechanisms. What we have is we have a first NAT that translates the virtual machine's IP from the tenant's IP address to the gateway's IP, to the compute node's IP address, which belongs to the compute node. This is still a private IP address. And then on the one gateway, it is translated again to a public IP. This is still... Then you will have to... we didn't cover this case specifically, but it will have to... The packets coming back might be lost. But new packets, new connections will work again because it will use a new connection, a new for tuple, and it will, the tables will be updated. Okay, so how this is done in a bit more detail. The virtual machine sends the packet. It goes to the integration bridge. The integration bridge detects that this is a packet that has to go to the internet. We detect this by seeing that this is not a network that exists in the tenant's overlay network. So the integration bridge applies a NAT. Here we use the OVS new functionality that was added, I think, in 2.6 of NATing a packet. And then it forwards the information out into the internet. For packets coming back, we use also the connection tracking feature to detect to which tenant and network this packet belongs, so that we'll know how to unnat it. Because effectively we lose this information in the natting process. The rules are installed from the Dragonflow controller, but there's not a lot of interaction with the controller here because everything can be done using OVS and capabilities that OVS provides us. I'm going to now show a slightly more involved application. This is the DHCP. And in Neutron, what you have is that you have a network node, or I think they can use even namespaces, and you have a DHCP server running per tenant or per tenant network or per tenant network per compute node, depends how you distribute it. But in the end, you still end up having a DHCP server running at least once per tenant. And we wanted to solve this and make this still a bit more distributed. So in Dragonflow, you have a single DHCP Dragonflow application. It's not an agent per se. It's a DHCP Dragonflow application that runs once per compute node in the Dragonflow controller. The virtual machine, once it's set up, it requests a new IP address, so it sends a DHCP discover. The integration bridge detects that this is a DHCP packet, sends it to the Dragonflow controller. The Dragonflow controller, the DHCP app is registered for these sort of packets. It creates a DHCP offer. Yeah, a DHCP offer, and then sends the packet back to the VM. Now, this is still done completely locally because in addition to having a distributed database in the network, we also have a local cache on the local controller that contains all the information that belong to the tenant that is running the VMs on that compute node. Okay.
Thanks, Omer. Okay, so now I will share with you a benchmark results that we did for control plane a few months back. So our test plans was to first to baseline Neutron. We did not intend to optimize Neutron performance. We just wanted to check the baseline performance of Neutron in our environment so that we know how much Neutron takes, how much Dragonflow takes. So then we did a baseline measurement from Dragonflow. We got an environment of about 34 or 33 servers from a good friend of us in Strato AG, a web hoster in sorry? 39. I think some of them didn't work. Okay. Yeah, we have it in the next slide. So we got a few servers from Strato AG, a web hoster in Germany. And we did a baseline running on each server a Dragonflow controller, and then we did a 4,000 node scale test. We reached to about 4,031 Dragonflow controllers. We did not intend to measure data plane, so we didn't measure traffic. Our purpose was to see how fast the network gets synchronized when you add a new port, when you have so many controllers. And the last test we did was to baseline Redis, which was using our database backend to see if Redis is a bottleneck in our test. So this is the baseline test. We have, you can see, one OVS and one Dragonflow controller running on each server. And we had 3 Redis shards, and with each one with one replica. On the 4,000 scale test, we created 130 OVS bridges on each compute node, each one with its own Dragonflow controller running, and the same Redis configuration. So total we had 4,031 controllers. One was running on the Dragonflow server. Our results were a bit surprising because both tests measured about the same. So we got about, when we tried to create 50 subnets on all those 4,000 controllers. So the blue boxes are the baseline test with just one Dragonflow per server. And the red is the scale test with 130 Dragonflow controllers on each server. And the results were about the same. So it was about, in this use case, in this case, was about a little less than 50 subnets per, sorry, a little less than 50 seconds to create 50 subnets. No, it sounds strange. And 1 port per subnet. It's the middle one, and then this is adding 5 ports for each subnet. I think I missed the slide with all the information here. Okay, so our conclusions were that Dragonflow performance was consistent with scale. It just remains the same performance even when the scale was multiplied by 100. The Neutron performance needs to improve. We didn't profile it, we didn't try to improve it, but this is something we need to do in the community. When we actually try to run multiple scripts for a test, running, injecting events to Neutron in parallel, and that improved the performance by 2.5 times. So it means that it is possible to improve the Neutron performance. The current performance is already production grade. It's faster than VM spin-ups. Now remember, we create about 3 ports per second. That's like creating 3 virtual machines per second, fully synchronized across the entire 4,000 nodes cluster, which is a lot. It's a very large network. It's about the speed of running a container, and it's scale agnostic. The Redis performance in the 4th test that we did proved that it wasn't in any way a bottleneck. It was able to push through 177 top-level network events. That means creating a VM or creating a network or creating anything from in Neutron. So it was able to push 177 and synchronize them across the 4,000 nodes. Here you have some information about the Dragonflow project. If you want to contribute, if you want to learn more, so we have some links here which you can take a shot and go later. So I'm finished. So if you have questions, please go. Okay, thank you very much.